if you remember, in the cylindrical coordinate, the height and the radius are still straight lines. Only the the height and the depth are straight lines, but the length are curved. But for the case for cylindrical spherical coordinate, we have only r is straight. Uh, Only r is straight, while the height and uh, the 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 height and the depth are both not straight. So the equation becomes slightly more complicated, but the way to derive the equation is pretty much the same. The theoretically, it's just that the numbers are a little different. Which not the numbers, I mean the radius, sorry, the length for everything is a little different, which is why we have a slightly different equation. So let's start with as before, we start with the QR first, in the heat going in from the R direction. Something is wrong with my, okay. Oh, okay. I'm not sure what is happening. Okay. In the R direction, and then this is QR going up. Okay, this is annoying. Oh, you couldn't see the ping just now because I was sharing the only the PowerPoint file. So sorry. Okay, but nobody commented, so I'm not sure whether you guys are listening or not. Okay, wait. Okay, can you see my pin screen?
Yes, doctor.
All right, thanks. Okay. So hopefully whatever the problem is has been settled. Okay. So let's try again. So for spherical coordinate, it's only the r direction is straight, and the length and the height are actually curved. Okay. So we'll see how this goes. So starting from the r direction, this is straight. So QR going in and QR plus dr going out. So for this case, we have the thickness is still dr. Okay, it's simply dr because this is straight. Okay, however, in the this time, even in the z direction, or in this case we will call it q theta. So we'll just call it something different so we don't confuse it with z, because when it's z, it's a straight line. So let's call it theta. You can call it z or whatever you want, but for simplicity's sake, because this is how the textbooks do it, so let's use just the same reference. So in this case, the height is no longer dz, simply dz. It's actually r d theta. Okay, so why we use r d theta is because to make sure that to compensate for the fact that it's curving. Okay, and then finally we go from and then finally we go from this direction. Okay, so this is q5. Okay, going out, then we have q phi plus d phi. So in this case, as we have seen, this is similar to the cylindrical coordinate where this part is curved. Okay, so this is actually in this case r sine theta. Okay, r sine theta d phi. Okay. So let's start again with the simple, start to recall firstly the general energy balance equation, which is heat going in plus heat that is generated equals to heat going out plus heat that is accumulated. So let's start with the easy ones, which is the rate of heat generated, which is Q times volume. Okay, so for Q times volume, Q is Q. Q is, if you remember, the average fluid average rate of heat for all in all directions. Okay, so so for volume, it's not simply, this time it's not simply dr d phi d theta, but we have to consider that for the r direction, then the thickness is dr. So but the height is, this time is r d theta, and the length here is r sine theta d phi. So as we just started, we can already see that it's a little bit different and complicated compared to the last time. So compared to cylindrical, and of course compared to the flat plate. So let's do the other one, which is rate of heat accumulated, which is equals to V times rho Cp d temperature over d time. Okay, so again we can substitute this, because this is the volume. So dr times r d theta times r sine theta d phi rho Cp dt over d time. Okay. So this is the simple part. So let's go for the rate of heat going in. So rate of heat going in is equals to Q in the R direction plus Q in the theta direction plus Q in the phi direction. So rate of heat out is QR plus DR, the difference in the thickness, then Q phi over d phi plus Q theta plus d theta. Okay, so actually I swapped this a bit here, but it doesn't really matter. You should get the same equation, just maybe a little bit different in the arrangement. So once again, we continue this by we solve for the rate of heat going out. First by using the Taylor series expansion. So it's the same as the cylindrical last time, in that QR plus DR is equals to QR plus dqr dr times dr, and then for q phi plus d phi is equals to q phi plus dq phi, but this is not divided by phi. It is sorry, wait, it is divided, okay, wait, it is divided by phi, d phi plus d phi, because this is just simply a change in the phi direction, and then for q theta plus d theta equals to, again similarly, q theta d q theta divided by q theta times divided by dq theta times dq theta. Okay. So we actually have everything already for the heat balance. So we substitute it into the total heat balance equation, which is the rate of heat in QR plus Q phi plus Q theta plus the heat generated, which is Q times the volume dr r d theta r sine theta d phi equals to rate of heat out. So rate of heat out is actually QR plus dr plus Q phi plus d phi plus plus Q theta plus d theta plus the volume sine theta d phi times density times the heat capacity d temperature over d time. Okay, so we use the terms that we got from the Taylor series expansion just now. Okay, so these three things can be substituted into here, here, and here. So the right side of the equation becomes QR plus DQR dr times dr. So tak? Okay. Plus Q phi plus DQ phi divided by d phi times d phi plus q theta plus dq theta divided by d theta times d theta. Then of course you have to don't forget about this plus no more space. Okay. Plus the volume dr r d theta r sine theta d phi. Okay. Rho Cp d temperature over d time. Okay, so as you can see here, we can actually cross this off because this and this crosses off, because if you bring it to the other side, it will be negative. So this can cross off and this can also be crossed off. Okay, so because we are interested in knowing the temperature profile, so the temperature profile is here. dT, the d temperature times d time, divided by d time. So let's isolate this term. So to isolate this term, we bring all this 1, 2, 3 over to the left side of the equation. So we will get okay, so we will get Q times the volume dr r d theta r sine theta d phi. Okay, minus because we brought the terms over to the other side, so it becomes minus dqr dr times dr plus dq phi d phi times d phi plus dq theta d theta times d theta equals to the term with the temperature profile just now, volume dr r d theta r sine theta times rho Cp d temperature over dt. Okay, so we have managed to isolate this, but we need to sorry, this is supposed to be negative, not positive. Okay, because everything was brought over to the other side, so this is negative. Okay. Brushes. Okay, So these are all negative. Okay. So now we can take the Fourier's law for all three directions. So if you remember Fourier's law, we have Q equals to minus KA dt over dt. Okay. Sorry. dt over dx or dr or whatever terms that you're using to express the distance. In this case, we are using r, theta, and phi. So for QR, we have minus k dt over dr, and then in this case, A is equals to since r is from here, so A is equals to the height times the length. So basically anything that does not involve dr, the other two dimensions that do not involve dr is actually make up the area. So we have r d phi, r sine theta, because this is the height and this is the length. The length. Okay. So for q phi, we have minus k dt over r sine theta d phi. Okay, so actually I forgot this term here. The d phi here. Okay, d phi. Okay, so uh, then because if you recall coordinates last time, the length is r sine theta d phi. The phi direction. So d over this times the area, which is dr sine theta d phi. Okay, so now that we have QR, Q phi, and Q theta, we can simply put it or all of these into here. We have this, and this. So now we can substitute all this into this, and this. Okay. So what we will get is Q. This is for heat generation. Q times the volume, R sine theta d phi. So now we substitute all the QR, Q phi, and Q theta just now. So we will get plus d over dr. K r squared dt over dr. So if you're wondering why there is if it's now positive because Fourier's law is negative just now, right? So r here is r squared because I took it out from here. So so originally dr is here, and then times the area. The area should be r d theta and r sine theta d phi. Maybe it's better for me to show. Originally it's like this. This is the area. Okay, so these two r's, I brought it into here, so it became r squared. You don't have to do it, but because if you see in the final equation that we have, the r is inside here for dr. So which is why to show you how I got exactly the same equation, I'm bringing the r inside. So since I brought the r inside, so this one cancels out. So we are left with dr times d theta times sine theta d phi. Okay, so we continue with the d phi, which is we will get the term for the phi direction. So we will get k over sine theta dt over d phi dr d theta d phi. Okay, so if you're wondering how I got the sine to be inside here, sine theta to be inside here, wait, is because previously from the previous the what do you call that the yes, because in the Fourier's law for the phi direction we have the term wait for the phi direction q phi, we have minus k dt over r sine theta d phi, then times the area dr r d theta. Okay, so what I did was I the r here cancels out with this r here. Okay, so we can have minus k sine theta dt over d phi times dr d theta. So this is how we got this equation. So from here, it becomes here, this here. And then the r cancels, the r in the r d theta cancels out with this here. Okay, so we are left with this equation. Okay, so I hope that's clear. Okay, so we continue with the theta direction. So plus d phi d theta, and then k sine theta dt over d theta. So again, how I got this was from the Fourier's law just now. We rearrange so we can get this equation. Then we have the term for the area, which is the area is d theta, no, dr d phi. So this d theta, it was already originally in the equation. Okay, so this equals to the term with the temperature profile, which is which is the volume dr r d theta r sine theta d phi times rho Cp d temperature over d time. Okay, so this is the energy balance equation. But to simplify it some more, so we can get the final equation that was in the slides, we can divide everything by the volume. So divide by the volume, which is dr r d theta r sine theta d phi, and we also divide by the term k. So what we can get is, no, I don't think there will be enough space for this. Okay, so if you divide everything by the volume and k, you will get, and then if you rearrange, you should get q over k, because we divided by volume, right? So plus 1 over r squared d over dr r squared. So we don't cancel it out just because we want to have the same term as the one that is shown in the slides. So dt over dr, no, dt over dr plus 1 over r squared sine squared theta, because we had other terms for that in outside the equation, so we just multiply them together, so we get r squared sine theta, sine squared theta, d squared t over d theta squared, plus 1 over r wait uh, uh oh wait, sorry, there was a there's only one sign. The r is squared, but the sign is okay. Sign is like this: d over d theta times sine theta dt over d theta. Similarly, we don't cancel it out, this sine theta and sine theta, because we want to have the same expression as the slides, the equations shown in the slides. And then finally we have the phi the phi expression, which is 1 over r squared sine squared theta. Okay, so I confused this with the phi direction, the theta direction just now. Okay, so 1 over r squared sine squared theta times dt squared over d phi. Okay, so equals to the equals to rho cp divided by k dt over dt. So if you remember, the thermal diffusivity alpha is equals to k over rho cp. So this can be changed into 1 over alpha dt over dt, d temperature over d time. Okay, so this is actually the equation that you have in the PowerPoint. So this is it. Goes to this. Okay, so is that clear? Or is there are there any more confusion with this? Because if not, we can just move on to our usual lecture. Any problems? Guys, are you still with me?
So far clear, doctor.
Okay, good. All right. So, as usual, if you don't, if there is anything that you don't understand, please let me know. Uh, okay. So for now, we'll just continue with our next lecture, which is what's the difference between this and this? Okay. Okay. So today we'll talk about we'll talk about convection, but we'll focus a little more on the forced convection inside the pipes. So our main the main things that we will be looking at today are the differences between free and forced convection. So we will touch on this a bit, because I believe we have already kind of covered this in the first few lectures. So we will also mainly talk about the boundary layer, dimensionless numbers, Prandtl numbers, and Nusselt numbers, as well as Reynolds numbers. So these are all dimensionless numbers. So later we will determine the heat transfer coefficient H using different empirical equations, and finally calculate the amount of heat transfer in a system. Okay, so I'm pretty sure you already know what convection is, but let's just revisit a little bit. So convection, there are two types of convection. So there are two types, which is natural convection and forced convection. So convection usually happens within a fluid, where the temperature differences, or if for natural convection, usually the temperature differences will cause a difference in the buoyancy of the the fluid. So it will become either lighter or heavier. So usually when when the where is it not full screen, I can see the bottom but whatever. um So usually for natural convection, the temperature difference will cause a difference in buoyancy. So for usually hotter fluid has is more buoyant. So meaning it is lighter than a cooler fluid. So it will rise to the top, while the denser, colder fluid will flow to the bottom. So this is why when there are differences in temperature in a fluid, so it causes the fluid to move, and we call it natural convection because it happens without any external forces. Okay, but for forced convection, is not simply it can be not according to the temperature difference, or part of it is because of the temperature difference, but there are external pressures acting on it, like using a fan. So we sort of push the fluid, either make the movement of fluid faster, or actually make it move in a different direction than it's supposed to. So we call it force because it's not natural. Okay, it doesn't occur naturally. So like I said, but the thing is, in fluid flow, how fluid flows is there are mainly two different types of fluid flow, which is laminar flow and turbulent flow. So for laminar flow, we characterize laminar flow by a smooth flow with not a lot of disturbances. While for turbulent flow, we have a lot of eddies or currents. You can imagine like small swirls of fluid, which is characterized by a lot of unbalancedness, and is that a word? Okay, turbulent flow, like the name is actually is caused by disturbances in the system. So whether the flow is laminar or turbulent, so we in this case we also call it film coefficient. Why do we call it film coefficient? So because if we are considering the convection is usually close to a surface. So for example, the surface of this water bottle, for example, so there is a surface here. So convection usually occurs within a fluid, which is the air here. So it can occur at the surface of this bottle. But right, if you focus right on the surface of the bottle, there is a very thin boundary layer which we call a film, where there is basically no movement of fluid. We assume that there is no movement of fluid, a very thin boundary layer. So because there are no changes in the velocity here, the main change in temperature occurs in the film, in the boundary layer, especially because the air has like we assume the air to be of a uniform temperature, but the temperature of the bottle might not be the same, especially if the bottle is being heated or whatever. So a lot of the change in temperature occurs between the fluid in the air and the hot bottle. Okay, so because there's a lot of yes, someone asked like a current. Yes, turbulent flow is like a current. Sorry, I belatedly saw your chat. So okay, so I hope that kind of explains it. So in terms of heat transfer coefficient, usually turbulent flow, the more turbulent the flow, the higher the heat transfer coefficient. So the more flow that a fluid experience, the change in the heat transfer increases generally. Okay, so how do we characterize laminar or turbulent flow? So like, how do I know this flow is laminar, or if this flow is turbulent? At what point do we call this turbulent, or at what point it goes into laminar region? So we can characterize this using Reynolds number. So Reynolds number is actually the pipe diameter, because in this case we are talking about convection in pipes. So the D is the diameter of the pipe, then the V is the fluid velocity, rho is fluid density, the density of the fluid, and then the fluid outside. In this case, in the case of my example just now, will be the density of air, and viscosity, mu is viscosity of air in this case. So so how do we characterize laminar flow? Laminar flow typically has Reynolds number of less than 2100. So if it's less than that, then we call the flow laminar flow. However, if the flow exceeds 6000, the Reynolds number is more than 6000, then we call this turbulent flow. So you might be thinking, okay, but that is 2100 and 6000. So there are about 3900 values that are unaccounted for. So this is what we call transition region. So we will talk about this a little bit more later on, but transition region is simply the change between the region where the laminar flow changes to turbulent flow. So we call this the transition region. Okay, so now first let's talk about the boundary layers that we discussed a little bit just now for a flat plate. So if we are talking only about the velocity of the fluid or the air, so we consider this system. So we consider this system. So before it meets the plate, this is the u is the velocity. So before it meets the plate, the velocity is uniform everywhere because it doesn't have any disturbances. However, once it meets the plate, there disturbances start to happen because the fluid right here that directly meets the plate starts to have perhaps friction with the plate. So there starts to become disturbances. So it starts to affect the velocity of the fluid. So you can see that as it goes from after it meets the plate and it goes from here and then to here, so you can see that there is now a velocity profile. So what I meant by velocity profile is that there is a change in the velocity. The velocity is no longer uniform. So you can also see the current. Just not someone messaged me okay, so anyway, it's like a current because of the differences, the disturbances. So here we can still call this a laminar flow. So laminar flow is, like I said just now, is mostly undisturbed, is smooth, the flow is smooth. And then there is a transition region where it starts to become starts to be affected by the disturbances. So and then finally we have the turbulent region. Here and you can see while here is all affected, here you can see that there is no change. The velocity is still sort of we can call it smooth because of the boundary layer. So this is we call this the boundary layer. So in the boundary layer, we assume that this is the flow the density is viscous. The fluid is viscous in that. We have this. So if we see this, instead of using velocity, we talk about temperature instead. So if we start with like in the bottle example just now, so we start with the fluid having uniform temperature, so it's not influenced by anything. So once it meets the plate, so we assume that this plate is hotter than the temperature of the fluid, or in this case we consider that the bottle is hotter than the air. So when the air starts to meet the fluid starts to meet the wall, the hot wall, there starts to be it starts to get heated up because heat transfer occurs, right? So we will start to have a temperature profile. So I believe this is pretty much straightforward. We call this the thermal boundary layer, where there is a change in temperature. Outside the thermal boundary layer, we have the temperature be the temperature of the air once more. So it's a uniform temperature once again. So what about inside of a tube? So how does this translate into tubes? So because in the industry we don't really use if we have the flow of oil, for example. So this all usually flows inside tubes, not on flat plates. So tubes would be more applicable for us to know as engineers. So for inside the tube, we have the fluid going in at a uniform velocity. So let's talk about velocity first, okay? So once it starts to go inside the tube, we can apply basically the same concept, but in this case we have two walls at the top and at the bottom. So because of the friction and whatever disturbances, here it starts to have we start to see the velocity profile here, because the velocity here is lower than the velocity in the middle. So of course this as it goes deeper and deeper into the tube, uh, the velocity profile starts to become more pronounced. You can see a clearer velocity profile. Okay, so in this region, the light gray region here, we consider this an inviscid flow region. So what inviscid means, sorry, 1 second. Okay, so if you remember just now, I said that in the boundary layer, we consider the fluid to be viscous, correct? So inviscid is actually the opposite of viscous. So we assume that it has no viscosity whatsoever. So as it goes deeper into the pipe, the inviscid flow region becomes smaller and smaller, and the boundary layer region becomes bigger until the inviscid layer does not exist anymore. So once the inviscid flow region does not exist anymore, we call this the fully developed region. So in the fully developed region, we have a fully developed velocity profile. Okay. So this is pretty much for the temperature profile is actually pretty much the same as the flat plate, where we have we consider this to be like two flat plates. What we see here is going in, it has a uniform temperature, the fluid has uniform temperature, and of course because the wall is heated, we will start to see a temperature profile. Okay, because and here the temperature near the wall will have a higher temperature compared to the middle, because the wall is heated, so heat transfer occurs to the fluid nearest to the wall first. So this is this would be the fully developed region, where there is no longer the inviscid region. So so this is we call this the thermal entrance region. So in the thermal entrance region, the inviscid fluid is still present. So once it's it can reach the fully developed region because it's an enclosed space. So but for a flat wall, a fully developed region does not happen because is open to the surface. So eventually it becomes similar to the surroundings. Okay. So for dimensionless numbers just now, so other than Reynolds number, we also have the Prandtl number. The I'm not sure how to pronounce this. So okay, so we characterize this by Cp times mu over K. So Cp is the heat capacity, the mu is the fluid viscosity, and K is the thermal conductivity. We also have the Nusselt number, where H is the heat transfer coefficient, I believe. Yes, H is the heat transfer coefficient, K is the thermal conductivity, and Cp is the heat capacity. So why do we need all these dimensionless numbers? Is because so that we can correlate because the flow is, to calculate the flow, we need to correlate all this. We actually use complicated empirical equations, so which is so complicated that we won't cover this in this course. But so that we can simplify and correlate all these equations, we use these numbers so that we can calculate the temperature profile, the heat or heat rate of heat transfer, and all those things. So if you're talking, so since we're talking about heat transfer coefficient, so we start with the laminar flow first. So we consider a tube with fluid flowing inside and then going out like so. So Tw is the temperature of the wall of the pipe. So Tbi is the bulk fluid temperature going into the tube, while TBO is the bulk fluid temperature coming out of the tube. Okay, so for laminar flow, in this case, for fluid flowing, for the equations that I'm about to tell you, for fluid flowing inside a tube, the Reynolds number must be less than 1000. Okay, so and the Reynolds number times Prandtl number times the diameter of the pipe divided by the length of the pipe must be more than 100. So these are the conditions where you can use the equations that this is the conditions that where you can use the equation, this equation, so to calculate the average Nusselt number. Average Nusselt number equals to the average heat transfer coefficient times diameter of the pipe divided by K. So we can use this equation. So usually what you are given are D, K, and stuff to calculate all the values use that you need to use to calculate everything else, and then you will have to calculate the heat transfer coefficient. Okay, so once you got the heat transfer coefficient, okay, so everything is actually other than the mu wall, the viscosity of the fluid at the wall temperature, everything else is considered to be at the condition of the bulk mean temperature, the mean bulk temperature, which is equals to the bulk temperature of fluid going out plus the bulk temperature of fluid going in divided by 2. Okay, so except for, as I've said, the viscosity of fluid at the wall temperature. So once you have the average heat transfer coefficient HA, you can use it to calculate the heat transfer coefficient. The rate of heat transfer, which is equals to HA times area of the pipe, times the average temperature. So the average change in temperature, which is T wall minus the bulk mean temperature. Okay, so that is for laminar flow. So how about turbulent flow? So for turbulent flow, we still use the Reynolds number to be more than 6,000. The Prandtl number between 0.7 and 16,000. And then the length of the pipe divided by the inside diameter of the pipe must be more than 60. So these are the conditions where you can use the equation that I'm about to show you. So if the values, any of the values fall out of the range, then this equation will not be accurate. So again, we are calculating the Nusselt number. So we can use this. You will be usually be given the diameter and the conductivity, the thermal conductivity, and then everything else to calculate this. So you can calculate the heat transfer coefficient based on the log mean driving force. So in this case, the driving force is the temperature. Okay, so the log mean driving force is called delta delta TLM. So LM stands for log mean and T for temperature. So how to calculate delta T log mean temperature is temperature of the wall, and this is the bulk inlet temperature, and then this is the bulk outlet temperature. So by calculating this, you can get the delta TLM. Okay, so but still if we fulfill other conditions, we can actually simplify the calculation a little bit more. So but this is only for turbulent flow in pipe. So if the flow is turbulent, and if the fluid in this case is air and is at the a total pressure of 1 atmosphere, you can use this equation to calculate the HL. So the if you remember just now, the very long equation just now is simplified to simply this. Okay, so it's a lot more simplified. So but if we are using the water as a fluid, and the temperature of water is between 4 degrees Celsius and 105 degrees Celsius, then you have the long equation become slightly shorter, which is this. And then if you're using organic liquids, we have the equation become this. And finally, if we are considering flow not in pipes, but in not in straight pipes like that, but in helical coils, we will have this equation. Okay. Earlier we were talking the flow between the between the laminar flow and the turbulent flow. So this is somewhere in the middle. So so this is as I've said before, if it's the Reynolds number is less than 2,100, then it's laminar flow. But if Reynolds number is more than 6,000, then it's turbulent flow. So we are accounting for the Reynolds number in between 2,100 and 6,000. So if we have this, we can use it. We can use this graph to calculate HA. So provided that we have everything else, the heat capacity, G is actually the mass velocity of the fluid given by the velocity meter per second times the density. So here is the inside diameter of the pipe times by g here divided by mu. So if you have this, you can calculate to get the x-axis value, and then from the x-axis value, as long as you have the length of the pipe and the inside diameter of the pipe, so you can use this. If for example the L over D that I have is 60, and I calculated dg over mu to be 3000, for example. So I can simply take a ruler and get the value here, and then from here get the y-axis values, maybe around 0.0035. So I have the value for all this. So all these terms equals to 0.0035. So if I have all the other values except the HA, I can calculate the value for HA. Okay, so what about flow through the tube annulus? So so in this case, before this we were talking about the flow going through the tube, the tube in the middle here. But what if the flow is actually flowing between the tube and the outside wall here? So just this small white white region there. So how to calculate this is we use a hydro. D is I did not see. Okay, I believe D is DH is the hydrodynamic diameter. So in this case is 4 times the cross sectional area. So as in we cut this, if we cut this tube, so the round section here there is the circular section is actually the cross sectional area divided by the perimeter of the tube. So we can use we can substitute this. DO is the outside diameter and DI is the inside diameter. So we can cross the things out, and we can get simply DO minus DI. So the outside diameter minus the inside diameter of the tube. So if we are talking about laminar flow, the Nusselt number, the inside Nusselt number will be HI times DH divided by K. So simply and then we can calculate the outside HO, the outside heat transfer coefficient, if we have NUO, and DH divided and also the fluid conductivity. So what we call this the entrance region effect, because if we remember just now, inside the tube, when the fluid has only started to enter the tube, there is the changes in velocity and temperature doesn't immediately take effect. So there is this is what we call the entrance region effect. So it just came into the tube and has not reached the fully developed region yet. So again, we consider the tube just now with fluid flowing in from here to here. So here, at the right at the entrance, the heat transfer coefficient is considered to be infinite. So, however, once the fluid has entered and travel a little bit inside the pipe, so we will have length over the diameter to be around 60. Then we can consider the heat transfer coefficient, to be HL. Okay, so Okay, so uh, in this case, H is the average value, average heat transfer coefficient value for a tube of a certain length, a finite length. However, HL is actually the heat transfer coefficient for a very long tube. So once the fluid has traveled within the tube far enough, so H will be approximately HL. So this only uh, applies if the length over diameter for entrance region effect only applies if L over D is between 2 and 20, because when L over D is 0, it's here, so H is infinite, but when it's 60, it's almost equal to HL. So is somewhere in between here that we still consider it to be an entrance region effect. Okay, so for this case, H over HL you can calculate using this formula. While this is really between 2 and 20 is really at the entrance. So between 20 and 60 is somewhere here, but not, the H is not quite equal to HL yet. So we can calculate using this formula. Okay, so yeah, H is the average value of tube of finite length, and HL is the value for a very long tube, the heat transfer coefficient value. Okay, so sometimes we use in the industry we use liquid metal. Um, so I don't know where it is. Okay, so in this case, sometimes we use in the industry we use liquid metal because we want to have a range of temperature. So for this um, for this what do you call that, for these conditions, it is actually beneficial to use liquid metal. But then for like we have talked about before, for if we have turbulent flow conditions, we can usually simplify the formula somewhat, and usually because in between laminar flow and turbulent flow can allow for a higher heat transfer. So usually in the industry we want faster heat transfer, correct? So usually in the industry we are using turbulent flow. So usually since liquid metal is usually used in the industry, it's usually used for turbulent flow. So we can actually consider the simplified approach. So if of course if it's in turbulent flow, then the Reynolds number will be equal to 6,000. So the Peclet number PNPE will be between 100 to 10,000, while the L over D is more than 60. Because if it's less than 60, if you remember the previous slide, we will be experiencing the the entrance region effect. So the fluid is the profile is not fully developed yet. So in this case, if it's more than 60, then the flow is fully developed. So we can consider if the heat flux is uniform, we can calculate the Nusselt number using this equation. So and then of course if we have D and K, we can calculate the heat transfer coefficient. While if we have a different conditions, so the Peclet number more than 100, but the temperature of the wall is constant, so that means the temperature of the wall doesn't change. So we can use this formula to calculate. Okay. So the Peclet number is simply the Reynolds number times the Prandtl number. Okay, so just now we were talking about the log mean temperature difference, right? So if a log mean temperature difference is because what we see is because when if the fluid is being heated or cooled, then the temperature is not, the mean temperature doesn't remain the same. So if we consider the fluid inside the bottle here, so at the moment, the mean temperature of the fluid the mean temperature of the water does not change. Sorry, it doesn't change. So the mean temperature is the same. So however, if I start to heat up this bottle, uh, maybe after 5 minutes, if it's a low temperature, perhaps after 5 minutes, the mean temperature of the water inside here is slightly more than at 0 minutes. Okay, then if I leave it for 20 minutes, the mean temperature will be different compared to the mean temperature at 5 minutes and at 0 minutes and all that. So that is why we need to consider the log mean temperature difference. Okay, so how you calculate this is the surface temperature, because we are considering the temperature change to be at the surface. So the inside temperature minus Ts minus outside temperature, divided by ln Ts minus Ti divided by Ts over minus To. Okay, so this is one way to calculate the fluid mean temperature. Okay, so if there are okay, so if we have flowing through, okay, but we want to have a difference in temperature, so we have outside the outside the tube, we have another bigger tube where we flow in either hot fluid or cold fluid, so that there are changes in temperature inside the inner tube. So for example, I want to heat up the temperature inside the inner tube. So I will, in the outside tube, uh, I will actually put in hot fluid, so it can help increase the temperature of the fluid inside the tube. So this is hot fluid. Okay, so but in this case, they want to cool down the fluid inside the pink tube. So in the pink tube is actually has hot fluid, and we want to cool it down. So what we can do is we flow in the cold fluid, so if heat transfer will occur between the heat transfer will occur between the inside of the tube, and then heat will actually flow outside the tube, so that the temperature of the cold fluid going in will, when it's going out, it will actually be higher because it has received heat from the fluid inside the pink tube. But the fluid inside the pink tube, when it comes out, it will be cooler than when it came in because it has transferred heat to the cold fluid. So
Basically, doctor, is like a heat exchanger.
correct, exactly. This is like a heat exchanger. So this heat exchanger uses this concept. So yeah, okay. I'm glad that you guys can relate this to heat exchanger, because this is exactly what it is. So but if it's in heat exchanger, usually we might have more than one tube. But let's just consider one tube for uh, uh, for the ease of understanding. So if you're familiar with heat exchanger, perhaps you're also familiar that with the co-current and counter-current flow. So for co-current flow, is simply that the outside fluid is flowing in the same direction as the hot fluid. So of course, in the counter-current flow, we have the outside fluid flowing in the opposite direction as the inside fluid. So uh, the temperature profile is actually affected by whether is the fluid is the flow is co-current or counter current. So you can see here for the temperature profile of the hot fluid, so it could, of course it goes down, and then for the cold fluid the temperature will actually go out. So the we can represent this by this that dt1 delta t1 and delta t2. So this is for a cold current flow. So this is temperature 2 at the beginning, and then temperature 2, the temperature of fluid 2 when it comes out, and of course the same thing for t1. However, for counter current flow, so like I've explained before, the temperature is the flow is in the opposite directions. So we have the you can see the temperature profile here is slightly different than the co-current flow. So we can still draw a similar representative with T1 and T2 here. So we can use the log mean temperature difference just now to calculate provided that we already have the heat transfer coefficient HL times the area of the tube. So this will be the area of the inside tube, because that is what we are concerned with, unless you are talking about the annulus, which is the outside. But if it's not the annulus, in this case we are talking about the inside tube. So this will be the cross sectional area for the inside of the tube. So times delta T Lm, so which is the log mean temperature difference. So but if we have the average heat transfer coefficient, then we can use the arithmetic temperature. So the arithmetic mean temperature can be calculated simply by delta T1 plus delta T2 divided by 2. So if you remember, the delta T1 is actually the difference between the temperature for fluid 1, and delta T2 is the difference in temperature for fluid 2. So this is quite simple, but if we are using the delta TLM, so we can use this formula to calculate the log mean temperature difference, so which is not that complicated either. So but something to note that delta TLM is always less than delta T as the arithmetic mean temperature. Oh God, we did finish quite early. Okay, yes, we do need to work on some examples. Wait, the chat. Why doesn't it come up here? Okay, so yes, we do need to work on some examples, and I plan to do so on Thursday. So I will be assigning an assignment by Thursday. So we will also on Thursday we will work on examples that are related to this lecture, while sometime next week, the assignment will be due next week. So uh, perhaps I will either after you have all submitted the assignment, so I will give you 1 week to submit the assignment. So this assignment will be based on all the previous lectures. So I'll give you until perhaps next Thursday to work on the assignment. So the next we will work on those assignment questions in the week after next. Is that clear? Wait, let me see. Mm, okay, so Uh, okay. Um, is it okay if we do you have any class on Thursday morning before my class? I know you have a class after my class, but do you have a class before my class?
I don't.
Okay, anyone has any class before my class starts? So
I
huh?
I don't, doctor.
Okay, great. If no one has any classes beforehand, is it okay to start? Because I'll finish. I have a bit. I have a meeting soon, so which is why I kind of finish a little bit early. So is it okay if we start the class a little early on Thursday, perhaps at 9 or 9:30, to compensate for the 30 minutes that we are going to lose here? Is that okay? Or do you guys not want an earlier class? So
Actually,
if you're
doctor,
okay, then we might have